Great. So today we're going to start looking at Chapter 9. Okay, Chapter 9, the first part of it at least is on some different ways you can graph things besides just y equals and then typing stuff in. There's other formats that are helpful for graphing different kinds of things. Like a picture like that would not be very easy to do with y equals. Okay, y equals is set up to draw functions. Okay, functions pass the vertical line test. This graph definitely does not. So it would be very difficult to draw something like that in y equals. Okay, here's another picture. It kind of looks like a butterfly. And again, that's a very difficult picture to draw as a function because it fails the vertical line test. And there's another one, a little simpler than the one before it. Okay, but we're going to start looking at all different kinds of graphs you've really never seen before. So it takes a little practice getting used to. Like I'm sure, like if I showed you guys a y equals x squared graph, you already kind of know what it should look like. Parabolas have, that U shape or an N shape. Well, we're going to have to kind of practice getting used to what these kind of graphs look like. All right, so we don't get into a ton of depth with parametric. We really only cover like parametric for 2 days, and then that's it. So it's just kind of a little bit about it, but there's a lot more stuff we could get into. All right, so I'll try to explain what it is first, and then a big part of it is how do you do all this on the calculator, okay, which we'll get into. All right, so the first thing that's going to be a little different about parametric is that to draw any of those things you see up there, they all have 2 equations. Okay, so there's 2 equations that describe the first one, 2 that describe the second, 2 that describe the third, instead of just a single equation. And what the 2 equations basically are is you have one equation that describes the x values, and then separately an equation that describes the y values. Right? So you're describing the x and y values separately, not one combined function. Okay, that's the big idea with parametric. So those 2 functions that I just mentioned, one that describes the x's, one that describes the y's, I'm going to call them function f and g. And when we draw parametric graphs, we have to define what's called an interval. It's kind of like on a window when you say, like, what's the lowest and what's the highest value? Well, if I just go to an example, here's 2 functions. One is describing the x's, one is describing the y's. And there's an interval that this value is allowed to go between. So in this particular problem, t is the variable, and you are allowed to plug in anything for t between 0 and 1. Okay? So what we're really doing with the interval is it restricts the domain. It tells you what you are allowed to plug in. Okay? It's not that if you plugged in a number bigger than 1, you would have something weird happen, like divide by 0 or square root of a negative. It's just they don't want you to go past 1 for whatever reason. Okay? And that interval is something you need to tell the calculator when you graph. Right? So we have 2 functions. They're always defined on an interval, which is like a domain for the variable. And if you take all the different ordered pairs that you could get by using function f and function g and plugging in the numbers you're allowed to, you get a curve. Right? What we call in a parametric graph a curve. Now, strictly speaking, don't think curve really means it has to curve. Curve just means image or picture. Technically, a line segment in parametric graphing is called a curve. Anything you see, these are all curves. These are all different parametric curves. So the 2 equations, okay, f, which is describing the behavior for the x values, and g, which is describing the behavior for the y values, those are called your parametric equations. Okay, so really important. Anytime you want to draw something parametrically, you have to tell me 2 equations. One for the x's, one for the y's. And now, whenever we use parametric, we always use the variable t. Just like when you use y equals, you always use the variable x. I mean, you can use other variables, but x is the most common one. Same thing here. We're going to stick with t. And when we get to the calculator, you'll notice there's a button here that says x, t, theta, and n. Well, this button does different things depending on what mode you put your calculator in. So if you keep it in function mode, it'll do an x. If we change it to parametric, it will do a t. So we'll talk about changing the mode in a minute. And you can think of t as a variable, because that's what it is. But when we talk about parametric equations, they call it a parameter. Not really sure why they give it a different name. But the idea is that it's a parameter it's a little bit more restricted than a variable. They're always going to tell you what you can plug in. That's part of it. Okay? Sometimes it's 0 to 1. Sometimes it's 0 to 2 pi. You'll start seeing like pi and 2 pi come up when we start doing things with sine and cosine. Okay? That's usually where that comes up. Okay, so any questions on the kind of the overall idea? Two separate functions, one for x, one for y. All right, so let's actually just look at the calculator for a second. So what I'm going to do is I press mode, and I'm going to put it on parametric. Now, when you press y equals, you're not going to see y equals anymore. You're going to see parametric. Okay? You see x sub t and y sub t. And on the screen right now, I see about 5 different equations that I can do. Maybe I could go down further and do more. But notice, to draw the graph in blue, go back, you need an x equation and a y equation. To do the one in red, you need to tell it an x and a y. If you leave one blank, it won't work. That's like having me telling you to graph the point 3, comma, question mark. You don't know where to put it. So you got to make sure you give it an x and a y. When you press window, you notice that some things are familiar there. But there's a couple things there that we've never really seen before. Anybody see something there that we haven't really talked about before? Yeah?
T min and max.
T min and max. Okay, we've got the x min and max, y min and max. We've done all that. But T min and max. All right, so T min and max has to do with your parameter. It's that interval I was talking about. What's the lowest value you're allowed to plug in for t? What's the highest? And also this t step. I'll talk more about that when we draw a picture. But it basically, t step controls the amount of detail that you see. Too much detail, and it's going to take a very long time to draw the picture. In fact, it might even freeze. Too little detail, and it's not going to look the way it should. Think of like if you were drawing a circle. And let's say I said, all right, I'll give you 5 points you can plot to make a circle. Well, if all you can do is 5, that's about as good as you can do to make a circle. Okay, it's going to look more like a pentagon. But if I said to you, you can do 20 points, well now, you've got more detail. Probably not 20, but you've got enough points that you can make more detail. And that's, if you start connecting these, it's going to look much more circular than if you connect these. So that's what t-step basically controls. How many points are being plotted to draw what you want to draw. Becomes a bigger deal when you draw things that are curved. If you're drawing a line segment, well, as long as you get the start and the end point, you don't really need any in the middle. Okay? You can put as many as you want. It's not going to really increase the quality of the picture. Okay? All right. All right. So if you have a curve that's defined by a pair of parametric equations, then another way you can say that is the equations give you a parametrization of the curve. You've parameterized the curve, taken it from maybe you had it drawn in y equals, and you rewrote it parametrically. Okay, and we'll talk about how to do that. Okay, like right now we have equation for a parabola. Well, maybe I want you to try to draw a parabola parametrically. So you would have to parametrize the equation for a parabola if you want to draw it parametrically. And it's actually very easy to take something that's not parametric and turn it into parametric. Very, very easy. The other way is a little harder. It's kind of like the difference between foiling and factoring. Foiling, very easy. Just first, outer, inner, last. Factoring, going back, can take a little more guesswork to figure it out sometimes. But we'll talk about it. That's kind of what this is like. Okay, curves can intersect themselves. Okay, that usually doesn't happen when you draw in y equals. Think of parabolas, any polynomials, they don't cross themselves. Sine, cosine, tangent, secant, none of those. They don't cross themselves. Okay, but these can. Right, so when you have a parametric curve, one thing about it that's a little different than a function is there's a start point and there's an end point. Parametric curves don't go on forever. Sometimes, if I go back for a second, sometimes parametric curves, they loop back on themselves and just keep tracing over the same pattern. Like these kind of graphs, if you kept drawing it forever, you wouldn't notice anything more because it would just keep looping over itself, okay, drawing over the same spot. But if we were to draw something like a spiral, spirals don't loop back on themselves. If you continue drawing a spiral, it just continues to get bigger and bigger and bigger and bigger. But the point is, it still would have a start point and an end point somewhere. Okay? So where they start and where they end depends on your interval. Okay, so where they start and where they end depends on what are you allowing me to plug in for the lowest value for t? What are you allowing me to plug in for the highest value for t? Let's say we had an example where the lowest value you could plug in for t was a, and the highest value you could plug in was b. In a real problem, it might be 0 and 1, or 0 and 2 pi, or it could be anything. So the way you find the endpoints is you have to do 4 calculations. You have to do a calculation for the x-coordinate of the start point, the y-coordinate of the start point, the x-coordinate for the endpoint, the y-coordinate for the endpoint. So four separate calculations. Okay, so if you wanted to find where a graph starts, you take the lower value, or it's usually lower, a, and you would plug in a into the equation for x and into the equation for y. So just to kind of give you an example, if I wanted to know where this graph starts, I would plug in 0 for t in both those equations and do it out. If I want to know where the graph is going to end, I take the second number, I'm going to plug it into the x equation and plug it into the y equation. So in this problem, I would plug in 1 for t here and there. And that would tell me where the graph ends. What does it do in the middle? Well, that's a little harder. It's kind of like in Algebra 1, if I gave somebody that versus that, they might not know the difference of what it looks like. But you guys should know it just because we've practiced a lot. Parabolas look like that, cubic ones look like that. So how do you know that? Just practicing and experience with it. So we'll practice with this a little bit and see what this kind of looks like. Is it, it has a start and an end point, but is it a curve? Is it just a straight line? We'll see. Okay, so any questions on that idea? That's the first thing we're going to do. Just practice finding where a curve starts and stops. Okay, so let's try. So here's our parametric equations. X equals 1 minus 2t, y equals 2 minus t, and the interval that you are allowed to use for t is 0 to 1. So you can plug in anything from 0 to 1, and the brackets mean you can include 0 and 1. Okay, so let's find the endpoints of the curve. Okay, so let's start with where this curve is going to begin. Okay, so Jayan, what number am I going to plug in for t in both equations to figure out where this curve starts?
Would you plug in 0?
Yeah, we're going to plug in 0. So I'm going to plug 0 into x, plug 0 into y. We'll get those two numbers, and we'll write it as a coordinate. Okay, so if I plug 0 in for t in the x equation, Shauna, what do I get for x?
1.
Yep, you get 1. So this graph is going to start at 1, comma, and now let's plug in 0. I'm sorry, yeah, plug in 0 again, now use the y equation. So Dylan, if I plug 0 in for t in the y equation, what do I get? 2. So this graph is going to start at 1, 2, and it's going to end somewhere. So we have to figure out where it ends. So Gracie, to figure out where it ends, what number do I plug in for t? We're going to plug 1 in to the x equation and the y equation. Right, so Megan, if I plug in 1 for t in the x equation, what do I get? 3. So what are we plugging in for t again? Yeah, we're plugging in 1. What's 2 times 1? 2, and then 1 minus 2. If it was plus, you would have got 3, but in this case we get negative 1. All right, so there's my x value of the endpoint. And Leo, what about my y value for the endpoint? Would be 1. Okay, so this graph is going to end at negative 1, 1. Okay, this is a simple enough graph, it's probably worth plugging it in, graphing it, and seeing it. Now, the start and end point is something you can only see as it's drawing it. Because once it's done, you're just going to have a picture on the screen. You won't know which end it started at. So we just have to watch it. It's going to start in quadrant 1, and it's going to end in quadrant 2. So it's going to kind of draw right to left. That's how this one will look. All right, so let's make sure we're in parametric, and I am. T-min and T-max, that's right here. T-min, T-max. So we're going from 0 to 1. Now the T-step is basically what's it going to count by. So just to make it simple, if I put it at 0.1, that means it's going to plug in 0 to plot a point. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. It's going to plot those, I think that was 11 points I just said. Now, if you did something like 0.01, okay, what it's going to do now is it's going to count from 0 to 1 by hundredths. So it's going to plot a point at 0.01, 0.02, 0.03, 0.04, 0.98, 0.99, 1. So it would plot close to 100 points to draw that picture. Okay. If I did something like this, what it's going to do now is it's going to plug in 0 for t, 0.5 for t, and then 1 for t. So now it's only going to plot 3 points. If this is a line segment, that's fine. If this is a curve, then you're only going to have 3 points, so it wouldn't look very good. So let's go like 0.1. So we're going to plot between going from 0 to 1 in increments of 0.1. I already know the start and the end point. So I think if we just go -4 to 4 on everything, that's big enough. Okay, and as we hit graph, we're going to watch it draw from quadrant 1 to quadrant 2, okay, start to end. You have to type your equations in first. So we have 1 minus 2t. Again, if you're wondering how you get t, you just press what used to be the x button. Okay, so 1 minus 2t and 2 minus t. If I don't type one of them in, the same thing will happen that just happened when I didn't type any of them. You've got to have both of them to make it work. And there's your graph. And if you watched it quickly, it drew from quadrant 1 to quadrant 2. Okay, so it's a line segment. And that's it. Any questions on how we graph that? Now, if you watched it, you noticed the speed at which it graphed. Let me set the window to 0.01. Okay, so now it's going to go from tmin to tmax in increments of hundredths and graph every single point it finds. So basically, it's going to plug in 0.01 for x, 0.01 for y, write the coordinate, graph it. Then it's going to go up 100. Do it again, okay, all the way until it gets to tmax. And look how much slower it draws it. Okay, much, much slower. Now, if you get to something like you accidentally type 0.0001, now it's going by tenths, hundreds, by 10 thousandths. Okay, it's going to almost look like it froze. Okay, it's because what it's doing now is it's graphing, it's plugging in numbers from 0 to 1, every single possible number for t, going by 10 thousandths. That's going to take too long. So if you run into something like this, just press second off, and the little circle that indicated it was drawing stopped. Now I can go back and draw, or change my t-step. Now, if you do something like 0.6, that's going to be a little bit of a problem. What are we starting at for t? Yep, starting at 0. And if we go in increments of 6/10, what would be the next number for t after 0? Jane?
Could you say that again?
What would be my next value for t after 0?
Would you use the 0.6?
It would be 0.6. And now, what would be the next one after 0.6 if we could do it? Leo? 1.2. 1.2. But where do we have to stop? What's our Tmax? Tmax is 1. So what's going to happen here is we're not going to get a full picture. It's going to plot a point at t when t is 0. It's going to plot when t is 0.6. But it can't plot anything after that. So look what happens to the picture. Okay? It was bigger than that before. So to avoid that happening, what I usually do is try to pick a t-step that divides into the tmax. 0.1 is fine, 0.2 is fine. In this case, 0.5 would be fine. But 0.6, that's no good. All right. So let's put it back on like 0.2. There's perfect. You'll notice that more when you draw circles. If you pick a t-step that doesn't divide into tmax, you're going to get a bunch of points for a circle, and then it's going to look like that. You're going to have a gap, okay? Because it's not going to be able to finish it because the next t-step would be beyond the tmax. Yeah, question?
I figured it out. Thank you.
Okay, so any question on finding the start and end points, or a little bit with graphing? We'll do a lot more with graphing as we go. Okay, but there's really no separate lesson I'm going to give you on how to do things on the calculator in parametric. I'm just going to kind of show you stuff as we go. All right, so sometimes what we can do is eliminate the parameter. So what that means is we're going to take something that's written parametrically, we're going to get rid of the t, and we're going to turn it back into the kind of equations we're used to. And I'm just going to kind of go through an example with you, and We'll see what happens. Okay, so let's take our example. And when I'm done, my goal is to have something like this. I want y with x as the variable. I don't want an x with a t as the variable, and I don't want a separate y as the t with a variable. I want to merge those together so I have a y with x as the variable. So if you look at the second equation, it's kind of what we want. It has y, but it doesn't have x as the variable. It has a t. Any thoughts on how I can get rid of that t using something else that's up there? I somehow have to get rid of what's in that red box. Yep?
Could you get t by itself on the other side
Mhm.
and then plug that in for t?
Exactly. So we're going to get t by itself in the x equation. That's step one. Get t by itself in the x equation. And then step two is to plug that into the y equation. So if you want to write that down, you can, but I'm just going to go through the example with you. So subtract 1, divide by -2. Okay, and we can clean this up a little bit so it doesn't look quite as messy. What number is in front of x even though we don't have it written? 1. So what I'm going to do is write this as -1/2 x. So that's what that really is, -1x divided by -2. And then -1 divided by -2 is +1/2. Okay, so I just divided out the numerator. Okay, so now we have a formula for t. And now plug it in. And that's how you have to do it every time. Solve the x equation for t, and then substitute that into the y equation. So get y equals 2 minus t. Now be careful here because it's minus t. Whatever t is, it's minus the whole thing. So it's a good idea to put t in parentheses, just in case you have to do a distributive property like you do here. So -1/2 x plus 1/2. Okay, so my final answer, I get y equals 2 minus 1/2. So I'm going to do that step out. 2 minus 1/2 is 1.5. And distribute the negative to the -1/2, and we get +1/2. And there's an equation that merged the two parametric ones back together. Okay, so now we have a function. Y equals, in fact, y equals mx plus b. What kind of, I know we already drew it, but what kind of shape is y equals mx plus b? Yeah. Yeah, it's linear. And we just drew it right here. Okay, so what I'm going to do now is I'm going to type that in. And I'm going to see if I get exactly the same picture that I have right here. What I'm going to do is I'm just going to put it on a new page. Okay, so we remember this is the parametric. Your calculator doesn't tell you what mode you're in up in the top anywhere. Kind of nice if it did. So I'm just going to label it so we know it's parametric. Okay, let's go back and type in 1/2 x plus 1.5. So I need to change my mode back to function. Now when you do that, what you had for parametric is still there. Okay, it's still in the calculator if you go back to parametric. It doesn't get rid of anything. All right, so 0.5x plus 1.5. I'm going to check my window because in order for this to look the same, I want to have the same window I had for parametric. So -4 to 4, hit graph. And let's compare that to what we just had. That's as a function. Okay, do those look the same?
is within the function?
It's part of it, right? The parametric had a start and a stop. A function doesn't, right? It kept going. Where this should really start is 1, comma 2. And where it should have stopped was -1, comma 1. We should only be seeing the section between those dots. So what we have to remember when we draw something as a function is that the original curve is usually just part of it. Okay? We were restricted. Why were we restricted? Because of this. We had to stay between 0 and 1 with my t. So what did that really mean for x? X was between -1 and 1. Okay. Those were my values that limited the lowest and the highest that x could go. So if I really want to draw that, the best I can do is tell the calculator to stay between -1 and 1. Right? So what I can do is something like this. Put that in parentheses. And then next to it, tell it, I only want you to do it when x is greater than or equal to -1. Let's start with that condition. Okay, I can't do anything about it drawing on the axis. That's the best I can do. But at least it doesn't draw the line like we had it. And I have one more condition, which has to be in parentheses. I want the graph to stop when x is 1. So x, second test, actually it's less than or equal to 1. Okay, so now here's my graph, and that's about as good as I can do. Okay. Pretend that the part on the x-axis isn't there. Okay, so here's our, let's put this one over here. This is our function with a restricted domain. And now that and that should look pretty much the same. Any questions on that? I know this one looks a little bit more jagged. That one doesn't look as jagged. I can't really do anything about that. Okay, but that's your graph. All right, so now we'll practice eliminating the parameter, but keep in mind you've got to put in that restriction as part of your answer. What should you be between? How do you know? Well, that's what we just went through. Figure out your lowest x value and your highest x value. And that's what you have to stay between. Okay, so let's try this one. So it asks us to eliminate the parameter, but there's a restriction. So make sure we carry that restriction into our final answer. Okay, so when you're done, you should have something just like this. Y is a function of x equals, put your answer, and then right below it, you should have a restriction on the domain. And I put less than or equal to's because there's brackets. If these brackets were parentheses, I would do that. All right, so let's just start with getting our function. Okay, what's my first step to kind of merge these two parametric equations back into one? Yep.
Get t by itself in the x equation.
Exactly. Get t by itself in the x equation. And what would t equal?
X plus 1.
X plus 1. Okay, so this is step one. We got t by itself in the x equation. What would I do next?
Plug what you got from the t equation into the x equation where t is.
Yep. Plug this in right there. So we're going to get y equals y of x. Same thing. Y equals x plus 1 squared. So we have a parabola that's been shifted to the left 1 unit. But it's not a full parabola. It's only a small section of it. So let's figure out where we start and stop. So the restriction is on x. You always restrict the domain. So as far as the y equation, you don't need it. We just look at the x equation. Okay, Jane, what value should I plug in for for t first?
The 0.
0. So if you plug in 0, what's 0 minus 1?
Or -1.
Negative 1. So this is a parabola that's between -1 and, now plug in 3. What's the highest x value that I'm going to get? 2. Now, on the calculator, you can't type it in like that. Okay? Well, you can, but it won't work. Okay? So the way you have to type in a restriction on the calculator is 2 separate sets of parentheses. X is greater than or equal to -1. And then in parentheses next to it, x is less than or equal to 2. I've tried typing it as a compound, and the calculator just never seems to work. If you figure it out, let me know. Okay, but this doesn't work. So any questions on how we eliminated the perimeter and then restricted the domain? All right. So let's look at going the other way. What we just did is not always possible to do. Some equations, it can be very difficult to get t by itself. Like if I gave you something like x equals t to the xt, you're not going to be able to get t by itself there, no matter what you try to do. And the problem is having the t as a factor and as a exponent. It's going to be really, really difficult. So I wouldn't give you something like that. But no matter what you come up with, it's always possible to take an equation, like you have in Algebra 1, and turn it into a parametric equation. So we can always write a function parametrically using what I'm about to show you. I'm going to go back to a problem that we already did, and I'm going to turn it back into parametric, but I'm not going to do it the way the original problem was. Okay, so what this means is there's more than one way to turn something that's not parametric into parametric. I'm going to give you the easiest way. Okay, but let me just go back for 1 second. Let's take this. Yeah. So this can be turned into parametric using those two. Another way you could do it and get exactly the same picture is doing this. X equals t, and y equals x plus t squared. And if you're like, well, how does that work? Well, let's look at what I did and change it again. Solve the x equation for t, just like we did up above. Well, this one already is. T equals x. Then once you get t by itself, take whatever you have on the other side and plug it in for t. I'm sorry. Wait, I messed something up. X equals t, y equals... What did I do? Did anyone see what I did? Yeah, I'm trying to do it, so I'm going to show you in a second, but I just... Yeah.
Shouldn't it be that the x and the y equation turns into a t and 1 just stays 1?
Yeah, so this should be... Yeah, the original problem had t minus 1. I was looking at the final answer, so forget the final answer. You wouldn't have that if you were doing a problem. So t minus 1 is what it should be. So let's see, y equals, let's keep that t minus 1. Okay. No, that's what it is. And let's make this t think I need to make one small adjustment, and then I'm good. Okay, does that work? Okay. I think that works now, because now we've got t by itself. So you take what's on this side, you plug it in right there, and you get y equals x plus 1 squared. Why did I? I think that works. Yeah, I had to adjust the sign. So it's a little tricky to figure out sometime, but the idea is all you have to do is let one of the equations equal t, and take the other equation and just change the letter that you have into a t. Now if I substitute in what I have here, t equals x, I get x plus 1 squared. So there's a set of parametric equations here and here that are exactly the same as this and this. So it can be a little tricky to figure it out, but I think I got it. All right, we're gonna try that again too. All right, so the idea is you just let x equal t. So that's the first one. X equals t. And then the second one, all you have to do in your y equation is change your variable to t. So it's kind of a cheap way to make it parametric, but it works if you do it right. Okay, so let me get rid of that. Let's try it on this one. Okay, so I want to turn that into, bless you, parametric. So looking at the formulas on the left, what does it say to let x equal? T. It says to let x equal t. So there's my first one. And now, how do I get the y equation? What am I supposed to do to get that one? Yeah?
Would you just write it normally except the x's are t's?
Yeah, just write the same thing, just make the x's t's. So 3t to the fourth plus 7t cubed minus 8t squared plus 2. And if you want to check your answer, follow the 2 steps. Get t by itself in the x equation, and then plug it in. Well, t is already by itself in the x equation. So take what you got on the other side of the x equals, just like we did right here, and plug it in. And you plug it in all the spots. And if you do that, you get 3x to the fourth plus 7x cubed minus 8x squared plus 2. So most of the time you wouldn't see parametric equations written this simply, because if you can just do this, why wouldn't you just do that? That's a lot easier. Okay? But that is a way you could always make something that's parametric, make it parametric if it's not. Any questions on that? Okay, does anyone want me to graph what's in the box and what's up above to see that they're the same, or people trust me? Okay. All right, so now we're going to look at a couple special shapes. Let's start with looking at a circle. Okay, first of all, just to compare this to a function, this is the equation of a circle as a function, where r is the radius of your circle. Now, if I want to type that into a graphing calculator, what do I have to do? Because you can't type this into a calculator the way it's written. I want to graph something as a function. What do you have to get by itself? Yeah, you have to get y by itself. So to do that, I would have to subtract x squared and then take a square root. And when I take a square root, how many answers do I get? 2. That's how you graph a circle as a function. So technically you can't. You have to graph the top part and then the bottom part separate. Okay. So let's just say I wanted to graph a circle with a radius of 3. plug 3 in for r. Let's see what we do. So we get the square root of 9 minus x squared, and then I have to type it in again. The square root of 9 minus x squared. Now, one thing that's going to look a little funny is that this screen is not square. It's a rectangular screen. So if you set 8 units left and right, and 8 units up and down, which is -4 to 4, it's 8 units, you're letting 8 units be in a wider space and 8 units be in a shorter space. What that means is it's really distorting how all your pictures are going to look. So if you really want to see this the way it should be, you have to set the ratio of width to height so that it looks square, and you can do that by pressing zoom 5. And that's as good as I can do to draw a circle, kind of cheating, it's in 2 parts, as a function. Notice it's got this gap in here. I can't really fix that. It's so steep in that section, the calculator can't draw it. And we've seen that kind of stuff before. When it gets too steep, it just can't draw it. Okay? So we kind of get a circle. It doesn't really look that good. If you zoom in, you'll see that it's really not that bad of a gap. Like if you zoom in, it might start to look like it's closer. Yeah, now you can see it's really much closer than it was appearing. But with the limitation of the calculator, it just can't draw it correctly. Okay. And to me, it almost looks straight in that section. It's like it almost got too steep. The calculator doesn't have enough resolution to draw it. Okay, so kind of a pain to draw circles as a function. Let's look at parametric. So what I'm going to do first is, rather than try to describe the whole circle, let's just pick a point on the circle. Right there. Now, with parametric, how many equations do you always have? 2. What's the first equation describe? X. Okay. So the first equation needs to describe how far to the right you go. And what's the second equation describe? Y. How far, in this case, up? It could be down. How far up I go. What do you think I'm going to do here to figure out x and y? Yep.
Right triangle trig.
Yep. I'm going to make a right triangle. I'm going to just do trig on it. So normally we let theta be the angle, but in parametric, what's our variable? T. So let's let t be the angle. So I want to come up with a formula for x and y. We could just call the hypotenuse of the triangle r, since it's the radius. And let's start with finding a formula for x. What trig function would I use that would involve t, x, and r? Yep. Yep, cosine. Cosine of my angle equals adjacent over hypotenuse. And x would equal r cosine my angle. There's an equation for x that you would type in to your first line in parametric. Does anyone have a guess in parametric what the formula for y would be? Without setting up the whole thing again? Yep.
R sine t.
R sine t. So much more elegant than doing it as a function. You got all that square root stuff and it doesn't even connect. It's going to look perfect. And I can draw it all in one shot. I don't need to use 2 separate y1 and y2. I'm going to put all of this into x1 and y1, into the one parametric system. Okay, you just have to pick a value for r. Now, the parameter. If you're not careful with your parameter, you won't get a full circle. So when we do this in a second, we'll play with the parameter and see what does t have to go between. Okay. If you do 0 and 1, you're not going to get very much of a circle. Okay. It has to do with the period of sine and cosine. Okay. So let's find the equation of a circle with a radius of 2. Can someone give me my x equation? Yeah.
2 cosine t.
2 cosine t. And can someone else give me my y equation? Oh, Tanya?
2 sine t.
2 sine t. Okay, let's type this in and graph it, because this is going to be the first one that's had some curvature to it. So we can really play with the t-step. If we don't do it right, we might get something that looks like a polygon and not a circle. Okay, maybe that's what you want. Depends on what if you're trying to get creative and just draw neat stuff on the screen, you can do all kinds of things. But let's change to parametric. We're going to type everything into the blue equations. 2 cosine t, 2 sine t. Now, I'm going to leave my window, I'm going to make it -4 to 4. But remember what I said, it's not going to look circular if I do that, but I kind of want you to see that. So let's go -4 to 4, -4 to 4. I know it's a little bigger than I need. This is only a radius 2, but it's good enough. Okay, now I got to pay a little bit of attention to my mode. I'm in radians. What do you think t would have to go from what to get a full picture? Yeah.
0 to 2 pi.
Yes, 0 to 2 pi. If you don't let it cycle through the whole period, you're not going to get a good circle. Now, 0 to 2 pi, that's 0 to 6.28. Let's go by 0.1. Now, I said before, make sure you pick a number that divides into the t max evenly, where you're going to get a little gap. It's not going to be bad, right? It's going to plot a point at 6.2. That's going to be the last one it can do, because then the next one would be 6.3. So you're going to have a very, very small gap. Okay, it's kind of hard to see it, but it is there, very, very small. Now, if you want to make that look circular, do zoom 5. And that sets the aspect ratio so it looks circular. Let's figure out what the ratio is. So it's about 6.4 divided by 4. So 6.4 divided by 4. So the ratio of width to height on the screen is about 1.6. So if you ever want to make something look square, just set your y value and then set your x value to that times 1.6. And it'll make it look the way it should. Okay? So that's kind of a shortcut. So 1.6 is the aspect ratio. All right, so there's our circle. Now, let's back the t-step down a little bit. Let's go to 0.2. So now it's going to count in increments of 2/10. I think it still looks pretty good. Okay. Let's go to 0.5. What do you notice now? Yeah.
It looks like it has sides.
Yeah, it almost looks like it has sides because you're plotting a point when t equals 0, 1, 1.5, 2, 2.5, all the way up to 6. But then the next one would be 6.5. Well, we're supposed to end at 6.28, so now we've got a pretty big gap. That doesn't look good. If you wanted to make it look like a diamond, you could plot a point every quarter from 0 to 2 pi. I did pi over 2. Okay. Again, that's not really an accurate picture. It should look like a circle. So usually going by 0.1 is pretty good. Now, let's put it in degrees. We can keep the window exactly the same, but what should my T max be now that I'm in degrees? Yeah? 360. I highly suggest you don't go by 0.1. If you go by 0.1, it's going to plot over 3,600 points to get from 0 to 360. You could go by 1 degree increments. In fact, you could probably even go by 5 degree increments. And I don't think you'll be able to tell. Well, it's okay. But it looks pretty good. It looks better than it did when it looked like a polygon. That doesn't really look like a polygon. All right? So just keep in mind how much your t-step is. Okay. Any questions on that one? So that's a circle. All right, so notice in the example we have here, the domain is -2 to 2. The range is -2 to 2. But the domain for the parameter was 0 to 2 pi. That's a totally separate domain you have to keep track of. Or 0 to 360. Depends on which mode you use. All right, so we'll finish up now. We're just playing with some different graphs, see what they look like, and just trying to describe them a little bit. Okay, so let's find some graphs, complete graphs, so you don't have to sketch it by hand, just on the calculator. And let's start with this one. T cosine t, t sine t. What does that kind of look like? It's a little different, but what does it look like from what we did before? Yeah, kind of like a circle, but what's different?
The radius is t.
Exactly, the radius is a variable. So what do you think would happen if you try to draw something that has a variable radius? The radius gets bigger and bigger as you draw it. What shape would that be? Yeah?
Spiral.
It's a spiral. Yeah. Specifically, this is 2 revolutions of a spiral, 0 to 4 pi. So if it starts here, 1, 2. That's 2 revolutions. So that's what it's going to kind of look like. So let's type it in. So t cosine t, t sine t. And we're going 0 to 4 pi, so I need to go back to radians. Always assume radians if they don't tell you otherwise. So let's go mode, radians. Now, what's the highest and lowest that the cosine function goes? If you don't transform it, you just graph sine, what would be the highest y value it ever hits? Yep, a 1. So at the very biggest, this could be, let's pretend that, and it might not line up like this, but let's pretend that this came out to 1, and this came out to 4 pi. So the biggest radius you could ever have, if everything lined up just right, would be 4 pi. So, and the biggest radius is going to be on the right side of the screen, okay? Because if that's the center, the right edge is where it's going to stop, so that'll be the farthest point from where it started. So let's set our x max to 4 pi. I know it can't go beyond that. And everything else is going to be shorter. I'm not sure if -4 to 4 is good enough. Let's go -10 to 10 on everything else. Yes, I know this is going to distort the spiral. It's not going to look perfectly circular kind of thing. But, okay. So, one thing is my t-step is awful. Okay, I'm going from 0 to 12 counting by 5s. No. We got to put that back at 0.1. Not sure I'm going to stay on the screen. Not quite. So what I would have to do to find a complete graph is just set my y-min a little lower. Now we're good. So there's 2 complete revolutions of the spiral. Okay. On the test, I'd just be looking for what's the mins and maxes and the t-step. So just tell me those 7 things. All right. Let's look at this one. Okay. This one is very different from this one. The reason is, look at where the t is. If you have a t in front, something in front can just get bigger and bigger and bigger and bigger till it reaches some upper limit. Sine oscillates. No matter how big t is, you could let t be 1,000,000. I can already tell you the answer is between 1 and -1 for this part right here. So this is always between 1 and -1, no matter how big t gets, times 5. So this whole graph is always between -5 and 5. Can't go beyond that, because we have something oscillating between -1 and 1 times 5. So let's just set our x window. Let's go -5. Actually, let me type in t min and max first. So 0 to 20.5. Okay. X min, -5, x max, 5. Now, this part in the front, though, or this y part, can keep growing because of what's in front. That's going to oscillate between -1 and 1. But if everything lined up just right, let's say that was a 1, and t was 20.5. 5 times, let's just round it to 20. What's 5 times 20? 100. So this graph, if everything lined up perfectly, could go as high as, we'll say, 110. Let's go a little extra. Now, if everything lined up, exactly the opposite, let's say that comes out to a -1 times 100, -100. So the y values are roughly going to be between -100 and 100, but I didn't account for the 0.5. So let's just say -110 and 110. -110 and 110. Okay, let's hit graph. Okay, so it's staying between, should be -5 and 5. Okay, it looks a little squished to me, so what I'm going to do is, well, first thing I'm going to do is actually type in the problem, because I didn't do that. Everything else, though, is fine. So 5 sine t, 5t cosine t. Now it hopefully shouldn't look as squished. Here's our graph, staying exactly between -5 and 5. Kind of looking like a watermelon, maybe, or something like that. Here's our graph. Okay, so it does take a little work to play with the setup to get the right graph first. Okay. And there's the mins and maxes that I used. Okay, last one. Okay. The ones up until now, they don't have any special names that I know of. This one does. Okay, let's kind of look at it again. This part is trapped. Okay, the part that I just underlined is trapped between two numbers. It could go as high as 5 and as low as -5 if sine was 1 or -1. This part in front, it's unlimited. It can grow without bound. It depends how high you let t go. Okay? This part is totally trapped, okay, between two values. If everything lined up just right, the highest cosine could be as a 1. 1 times 5 is 5. 5 minus 5 is 0. On the opposite end, pretend cosine came out to a -1. Plug in the right number for t for that to happen. -5 times -1 is a +5. 5 plus 5 is 10. The y values here are trapped between 0 and 10. The x values depends on what I let t come out to. So let's try t from, let's go -50 to 50. Just picking something to try and see how it works. So we've got -50 to 50. Going by 0.1 shouldn't be too bad. I think if you were counting by tenths from -50 to 50, got about 100 points or so to plot. No, 1,000 points. Let's go by ones. So now we have about 100 points to plot. That's better. Y values, it's always going to be between 0 and 10. Now the x values are dependent on the parameter. Okay, if everything lined up just right, let's pretend that was a 1. So this would come out to a -5. And if this was 50, 5 times 50, 250 minus 5. So 245. -50, we'd have -250 minus 5. So it's always going to be around 250 plus or minus 5 or so. So let's try like -260. Leave a little extra. -260 to 260. And I think that'll be okay. You can go a little extra if you want. -275. If you want to do 260, it's fine. All right. Again, you have to type in your equations. So it's still drawing. See that little yellow circle? I was going to stop it if it didn't, but it just stopped. So -5 sine t and 5 minus 5 cosine t. That's one of the most frustrating things when you graph it and you get this like line and you're like, it doesn't look right at all. Either your window's wrong, something in the window, or you didn't type in your equations. All right, so let's see what I did. -5 sine t, 5 minus 5 cosine t. I'm in radians. All right, so what else can we try? Y's look good. X's, yeah.
Your x, you just put -5 sin t. It's 5t minus 5 sin t.
Yeah, your calculator is covering part of the equation.
Oh, 5t minus 5 sine t. Thank you. 5t minus 5 sine t. Let's hit graph now. No. Is that what yours looked like? All right, so we have the equations correct now, so that's good. We're in radians. Did anybody get anything that looked different?
Yes.
What did you get? Did it look kind of like? Yes, it's supposed to look like that.
Oh.
What did I do wrong?
That means I did it right.
Yes, can I see what you did? Let me see yours. Yes, it should look exactly like that. So I'll just 5t minus 5 sine t, 5 minus 5 cosine t, -50 to 50. Wow. Why does mine look like that? So if you type this in, you should get these curves that look like this. What's wrong with mine? 5t minus, oh, that's not a minus sign, that was a negative. See, it can be tricky. So what you get are these curves that basically look like this. Why do they look kind of jagged? Well, that's because the window step isn't good enough. Make them like 0.1. It's going to take a while, but now they're going to look nice and they're not going to look as jagged. Okay, so you get these repeating curves. So if you take one of these curves, just trace over it, and then flip it. Let me show you what you have. It's supposed to flip all together. Let's take it, flip it. That's what it's supposed to do. What you have right here is called the curve of quickest descent. and that's called a cycloid. What that basically means is that if you had a ball or any object and you wanted it to roll from one point down to the bottom, the equation for a cycloid is the fastest curve for it to get from a high point to a low point. If you said, well, what if I just put a board straight and had it roll down the board? No, the cycloid would be a faster curve. Okay, and that's called the curve of quickest descent. Okay, you don't have to write this part right here, the curve of quickest descent. You don't have to know that. Really, I just want you to know that it's called a cycloid. So in our problem, what you'd have to do is factor out the 5 and make it 5 times t minus sine and 5 times 1 minus cosine. And then it would look just like this. So that's called a cycloid. Just copy up to the wavy line. Okay, so homework tonight on parametric is page 481. I guess it's 1 through 1, 3, 5, 7, 9, 11, 13, 15. Why don't we just say 1 through 17 odd? That'll be shorter. So 1 through 17 odd, 21, 22, 25, 26, and 29 to 33.